Okay, so today we're going to finally get to this notion of a derivative. This is section 2.1 in the textbook. And so this is tangent lines. And the derivative. Okay, so before defining the derivative, we're going to give motivation for where the definition comes from. So, in particular, we seek to find the slope of a line that's tangent to the graph of a function at a single point. And in order to find a tangent line, we need to first define what's called a secant line. So let me be careful to draw this the best I can. Okay. So consider a function that might look like this. All right, so this is the graph of some function called f. And suppose we have a point on the x-axis called c, right? And then this point on the graph would be c comma f evaluated at c, right? So we just pick some c and we see that we have a point there on the graph of the function. And then if we introduce this notation of delta x is just some positive number, we can have another point, maybe I'll do it over here. So here, I'll say this is c plus some number, which I'm calling delta x. Okay. In general, when I write delta x, this is just going to mean the change in the x value. So change in x. That's what that means. So if I'm focusing on this point C, I can move left or right by some change, which I'll call it delta x. So I add delta x or I subtract it, and I'll move to the left and the right of that point C. So here, if I come up to the function, there is another point on this function that is evaluated at this. So this is the point c plus delta x comma f evaluated at c plus delta x. Okay. Now, if you remember from a college algebra or a pre-calc course, there is an equation of a line that connects 2 points, right? And these are 2 points. So there is some line that connects those points. And the slope of this line is given by the change in y over the change in x, right? So the slope of this line, which this is called a secant line, it's passing through 2 points on the function. So the slope of this line is given by, so m secant. This is simply your new y value minus your old y value divided by your change in x. If you remember the slope formula, just recall, I guess, so m is equal to y2 minus y1 over x2 minus x1, right? Your rise of your run. So how far did we change from here to there, which is that number minus that, which is just delta x. okay? So this formula, this difference quotient, is giving us the slope of this secant line passing through these 2 points. Okay. Now, what we're wanting is the slope of the line that only passes is tangent at that point. It doesn't cut through the graph, it's just touching it at that point. So what we want is this line. We want the slope of that line, right? And we'll get into why we want the slope of that line after we define how to find it. Okay? So suppose now that we want to somehow approximate the slope of this line. Well, m secant is an approximation to the slope of that blue line here, the tangent line, right? Whatever number that is somehow an approximation to the slope of this line. But we can get a better approximation by having a smaller change in x. So for example, if we picked a new delta x to move, maybe like here, so I'll call this like c plus delta x, I don't know, 2 or something, just to have a different change in x. Then if we evaluate the function at that point, we get a new point right there. And then if we apply the secant formula again with this new x, delta x2 instead of it, so delta x2, whatever, then we're going to find the slope of the line here. So you can see that by having a smaller change in x around c, we get a secant line whose slope, it looks a little bit closer to the slope of the line tangent at that point, right? Do you see that? How smaller change in x, it starts to look like the slope of the blue line? Good. So this is where the derivative comes in. In the previous lectures we've had on limits were needed in order to formally define this process. In particular, if we take smaller and smaller changes in x, we're hoping that the slope of the secant line converges to some number as that change in x goes to 0. As the change in x goes to 0, where are we converging to? Well, that's what we wish to be the limit. I mean, the derivative. So the definition. So the derivative of f at the point x, is f prime of x equals to the limit as delta x goes to 0 of the difference quotient, the slope of the secant line. Oh, I almost forgot an important step. provided this limit exists. So if this limit exists, we call this limit's value the derivative at the point x. Because remember, the slope of the tangent line, the slope is a numerical, it's a number, right? So if it's a number, then this is a value, it's a numerical value. However, so this is important to note, if f prime of x exists for all x in some open interval, maybe AB, then f prime of x defines a function in terms of x on that interval. So then f prime of x defines a function of x on that open interval, where the output of that function is the slope of the tangent line at that point for each of the points in that interval. Okay. So in particular, for this function here, for example, I can tell visually that the derivative would exist for all, looks like all real numbers. So f prime would be defined on all real numbers. And if you evaluate f prime anywhere on the real number line, it gives you the slope of the tangent line to the point above it, or of the function f. So as far as notation, I need to make some comments about notation. So f prime of x is just one way of writing the derivative. Another way would be if you have a function y of x somehow. Another way would be dy dx. So if you have like y is equal to x squared plus 1, then you can take the derivative of that and write it as dy dx. Or you can write it as y prime. Okay. I'm particularly fond of this notation here, dy dx. And you can read this as the derivative of the function y with respect to the variable x. You can also think of the derivative as what's known as a linear operator. You don't need to know what that means for now, but you can think of it as like an operation that you can apply to functions. And when you think of it that way, you can say the derivative with respect to x applied to the function x, or f of x. That's another way to define it. As an operation, you can apply to a function and get a new function, provided the derivative exists on some interval in question. But hopefully all of you can see that this limit is taking differences in x going to 0, applied to this picture here. We started there, we started there, we started there, we end up there, end up there. As that difference goes to 0, we're going to converge to some numerical value, which is precisely the slope of the tangent line at that point. Okay. So maybe we should work out some examples by hand, applying this definition, just so we can see how this limit looks. So we can say maybe find f prime of c where f of x is equal to 3x minus 1, and c is equal to 2. So let's apply this formula here and get out something. Right? So let's look at what happens here. So we're considering a single point C equals to 2. So we just need to look at this limit. So f prime of C is equal to the limit as delta x goes to 0 of the difference quotient. So f of this, right, is going to be 3 times 2 plus delta x minus 1. So that's like this piece here. And we need to subtract off f of the point in question. So 3 times 2 minus 1. And that's all divided by change in x. Okay, so here, like, this is the point in question. So wherever you see an x over here, you replace it with a 2. And this right here, that's like f at x plus delta x, right? You just substitute in x for that value. Is that clear? It's like putting in that value instead of just evaluating with x. And then here, this is simply f at x, where again, x is equal to 2 in this case. Okay, so let's figure out where this limit goes. I'm probably going to need some room. So we get 6 plus 2 delta x minus 1. And then we have minus all that stuff. So we have inside of here, we have 6 minus 1 is 5, right? And then we have minus that. That's all over. Oh, I almost forgot the limit. Very important to remember to write your limits. So it's the limit as delta x goes to 0, and I had 6 plus 3 delta x minus 1 minus 5 all over delta x. And then we get, if this is the limit as delta x goes to 0 of, so we have minus 1, minus 5, so minus 6, plus 6. So those go away, and we're left with those divide out. And then the limit of, so the limit of a constant is just a constant. So the derivative of that function at x is equal to 2, or c is equal to 2, is 3. Now, why does this make sense? Like we calculated it, but why does it make sense after in hindsight? What is the derivative at a point telling you? It's the slope of the line tangent to that point, right? On the graph of the function. What does that function look like? So in x is 0, we're like here. In x is 1, we're at like right there. So this is f of x equals to 3x minus 1. It's a line. So if you look at, in particular, this like 1, this 1/3, this is like 1, 2, right? And you go up and look at that point, what's the slope of the tangent line to that point on that graph? It's just the same as the slope of the function. It's a line, right? So the slope of the line tangent to the graph is going to be the same as the slope of itself. And what's the slope? 3. So obviously it should be 3 in hindsight, right? If you remember what this is trying to do, right? If you remember this is trying to find the slope of the line tangent to the point on a graph, then obviously any line that's tangent to a point on the graph of a line is just the slope of the original line. So it should make sense. Okay. Let's look at some more examples. Okay. Suppose we want to find the derivative as a function instead of just evaluating it at a point. So I can say find the derivative of the function f of x equals to x squared. Yeah, let's just say x squared. And we just, using this definition, we should be able to find out what the derivative is. Okay, so solution. So we just need to plug in. So prime of x is equal to the limit as the change in x goes to 0 of the difference quotient. So this is like saying x plus delta x all squared minus x squared all over delta x. Now this is our function evaluated at x plus delta x. That's our function evaluated at x, and there's our delta x. So everything matches up. So now we just have to expand this and do some algebraic manipulation to see what it is. So this will be x squared, and then plus 2x delta x, right? X times x and x times that, and then finally delta x squared, and then we have that minus term there, and then this is all over the change in x. So then we see x squared minus x squared, we're just left with these terms here. And then we have 2x delta x plus delta x squared all over delta x. But now we can factor out a delta x and fit it right here. And we get get 2x plus delta x. Then if we divide that out with limit as delta x goes to 0 of 2x plus delta x. And this limit is just this, 2x. Okay. So this now is a function. This limit always exists, right? So this function f prime of x equals 2x is defined on all the real numbers. So we have our original function, f of x equals 2x squared, and we have our derivative function equals that. And this can be nice when you want to know the slope of the line tangent at a point on f, right? So for example, like if I wanted to know the slope of, so this is f, right? That's f of x. If I want to know the slope of the line tangent to 2 comma f of 2, if I want to know that slope, then I just plug in a 2 into that and I see that it's 4. Okay. And again, I can't emphasize it enough that when you're calculating derivatives, you need to just always remember what it's trying to say. Right? You're trying to say something about the slope of that line tangent to that point. So you have to always remember that. It's going to be very useful later when you're developing algorithms and talking about optimization. Okay. All right. So what is next? So when considering how the derivative relates to continuity of functions, which we know what that is, right? There's another equal representation of the derivative as the original definition that I told you earlier. So this is, I would say, the alternative form of the derivative. Okay. Of the derivative at the point x is equal to c. I recall again in the back of our minds, we want to somehow relate this to continuity. Continuity is defined at a single point. So we're considering how the derivative and continuity related at this point C. Okay. So this alternative form is given by f prime of C equals to the limit as x goes to C of f of x minus f of C all over x minus C. And you can see that this should be equivalent, right? Like if I write the other form, right? Just so I can just verify it for you. Do you see that those are the same? Like, yes, it would require rigorous proof, but at least like intuitively they should make sense, right? What's happening here as delta x is going to 0? Where is this inside term going? It's going towards C, right? As delta x goes to 0, this term inside here goes to C, right? So up here, right, as x is going to C, this and this are basically the same, right? As x goes to C is the same thing as saying as that goes to 0. Okay? And then here, as x goes to C, this is going to 0, right? So saying that as x goes to C here is the same thing as saying that this change in x is going to 0. So they're the same. But this alternative form is useful because it implies a direction on the one-sided limits, right? Like as delta x goes to 0, that's fine, right? But here we can say that. So what does this say? This like definition here. It says that the limit as x goes to C from the left of this difference quotient needs to equal the limit as x goes to C from the right. Of the difference quotient. So these need to equal, and that would be the derivative of the point C. So these need to equal in order for f prime of C to exist. Right? In a previous lecture, we said that the limit exists if and only if the left and right hand side limits agree. So this limit exists if and only if the left and right hand side limits agree. Okay. So with this notion, now we can start considering continuous functions that might not have a derivative at a given point.
So we're saying that x minus c is always equal to delta x, is that right?
Well, in a sense, that's what you can interpret it as, right? Um, because like this is a difference in x. This is a change in x, right? And that's also interpreted as a change in x. So yeah, that's like an equivalent way of interpreting it. Right?
Okay, that makes sense.
Okay, so let's consider a function where the derivative doesn't exist. So maybe something like f of x equals to the absolute value of x minus 2 is not differentiable the e over there. So that is not differentiable at x equals to 2. So we can use this alternative form to kind of easily argue why it's not. So it's 0, 1, 2. So 2 is. So this is the graph of that. Okay. Now that's continuous. This is continuous at x is equal to 2. But it's not differentiable. Why? Well, how can we show this? Well, pictorially, we should be able to see it. So if we start looking at, let's look at the right-hand side limit here. So this is like our C right here. That's like our C, right? And we're picking x over here. So x is going that way, okay? So when we first evaluate the difference quotient here, that's just the slope, right? That's just the slope between there and there. The slope of the line connecting those 2 points. And then as we get closer, it's still the same, right? And as we get closer, it's still the same. So we can conclude that if we're going from the right, what is the slope of that line? It's just 1, right? We can say that the right-hand side limit, so as x goes to 2 from the right, of f of x minus f of c over x minus c, that's going to converge to 1. Just looking at the picture here in this case, and not working it out algebraically. So, what about from the left? So if we pick some value here, this is just the slope between those 2 points, right? Your y's and your x's. Which this slope has, what's the slope of this line here? And if we're going this way, pick that one, still the same slope, pick there, still the same slope. What's the slope? What's it converging to on the left?
-1.
-1, right? I should say 2. This is going to equal -1. So the left and right-hand side limits don't match up. So this limit's not going to exist. So you conclude that f prime at 2 doesn't exist. So this is something that I need to kind of come back on from a previous lecture. When I was talking about continuous functions, I said these are well-behaved functions, and I might have used the word smooth. Continuous functions don't have to be smooth. And I did mention that, but I shouldn't have ever said smooth at all. Continuous functions can have these creases like this. But continuous and differentiable functions are going to be smooth curves. There's no jagged edges, there's no gaps. These will be the nicest types of functions, continuous and differentiable. Because if you're going to have a derivative, you can't have those crimps in the graph. Because then the left and right-hand side limits don't match up for the derivative, and the derivative won't exist at those points. So one thing that might be useful for you to do, and I encourage you to do, is to try to think of other functions that don't have derivatives. Right? This is one example here. Can you think of other functions where this limit is not going to exist? Being able to construct such functions is actually a really, well, it can be a very useful tool. Constructing examples in mathematics in general is a useful tool. But for data science, yes, it will be a useful tool to be able to construct examples where things don't happen, right? Because suppose you have like some algorithm that works on these functions and you assume that it's always going to work and you just trust it, but there happens to exist functions that it won't work on. Then you should be able to try to at least construct those things. Okay, so on to the theorem now. So theorem. So it says if f is differentiable, x is equal to c, then f is continuous at x equals c. Okay. So this is actually a nice property. Now, just because you're continuous, that doesn't mean that you're differentiable, case in point. But if you are differentiable at a point, then you are continuous at that point. Okay. So differentiability implies continuity, but continuity doesn't necessarily imply differentiability. Okay. Now, let's go ahead and prove this. Again, whenever I write proofs on the board, I encourage you to think about them and to try your best to understand the logic behind them. But at this point in your education, you're not expected to be able to write proofs, nor will you be expected to write very many proofs in your later classes. You will have to prove some things, but not much. So I just encourage you to just bear with me when I give you these arguments. I'm just justifying why this statement is true. So we have differentiability implies continuous. So we want to prove that. So we assume the hypothesis of the statement. We assume that that is differentiable at x equals c. So assume f is differentiable at x equals c. Okay. And in the back of our minds, we should remember that a function is continuous at a point c if the limit as x approaches c of f of x is equal to f of c. So if this happens, that means f is continuous. So that's what we're going to work with. We're going to want to show that the limit of the function converges to f of c. And if we show that, then we've proven the theory. So then we look at the limit as x approaches c of f of x minus f of c. So just bear with me on this. If this limit goes to 0, doesn't that converge to that? Right? If this limit ends up being equal to 0, the limit of f of x must equal f of c, if that's going to be 0, right? Okay, so then notice that this limit is equivalent to saying the limit as x approaches c of x minus c times this divided by x minus c. All right, I just multiplied by 1, right? Multiplying by 1 doesn't change anything. That divided by that's just 1. So I did not change the original limit. But then by properties of limits, the limit of a product is the product of the limit. So this is going to be equal to limit as x approaches c, x minus c times the limit of the other part. Limit of the product is the product of limits. So now we see that this limit is 0, right? Limit as x goes to c, we just plug in c and it becomes 0. And we need to make sure that this isn't also infinity or something. But what do we know about this quotient here? This is the derivative, which we know f has a derivative at x equals c. So we know that is equal to f prime of c. That has to be equal to 0. The derivative, if it exists, is just some number. So then we have 0 times some number, 0. So what we've shown is that the limit here is equal to 0, which means that that must equal that. This limit equals f of c. And we've shown that f is continuous. Okay. This, if true, implies this, which implies it would be continuous at that point. So since this is equal to 0, that means that, which means that it's continuous, and we've shown the conclusion of the statement to be true. Okay. Okay. Okay, so I think this would be a sufficient place to stop and not continue anymore. And I guess I'll go ahead and stop the recording now.